There's a question about indefinite intervals. Go ahead.
Yes. The indefinite interval of e to the x minus...
Minus is up here?
No, e to the x minus e to the negative x divided by the same expression except there's a plus in the middle.
Isn't that good?
That's good.
Someone didn't like to look at this. All right, we're going to find the antiderivative of this. A couple of things. I guess the first thing off the record is that, again, there's not one, at least at this point, maybe at the end of chapter 7, but if I give you an antiderivative, particularly at this point, you're going to be able to substitute. Now, the question, of course, that you have to ask yourself, do I have the derivative of one of these functions? Is it the derivative of the other one? Right? And the numerator is the derivative of the denominator. The numerator is the derivative of the denominator. This screams that we should let u equal the denominator. It becomes 1 over u du. Finish the rest of this. So good. My math lab problem. Was this my math?
It did it a little different. It had negative x as u.
It had negative x as u. That's interesting. Okay. Then I'm going to definitely do it differently.
I didn't get that way.
Okay, good. Negative x as u. That's weird. Again, beat me to the answer. Then du equals e to the x minus e to the minus x dx. This becomes what? The antiderivative of the denominator is flat out u. The numerator is du. Okay?
Yeah, that makes sense.
And the antiderivative of 1 over u du is the natural log of u plus a constant. You don't need the absolute values here. This is always positive. And so it's the natural log of e to the x plus e to the minus x plus a constant. All right. Another antiderivative. Is that okay? I'll take other questions.
It can never hurt to include that.
No, it never hurts. Right. Particularly because that's right. It actually hurts me to not write it. Right. But you know, authors such as Stewart for his calc book, and I'm not sure if Briggs and Cochrane do it, but they say, well, you know, they always just make the assumption that u is positive. Yeah. Other questions about this? Other questions in general? All right. I'll always be coming in asking for questions first, okay? When we're doing some reviews, 6-2, area between curves, let's just do some exercises. What's that area? So I've been thinking about how I'm going to handle questions like this in the exam, okay? And so I'm probably going to just give you a picture. Probably just going to give you a picture. So, and again, this is a big change. This is a big change just in teaching, I think. That over the course of the last decade or 15 years, which is when I came to get my PhD and go through school as well, we went from an era in which it was impossible to get a graph, right, like this, in order to teach it well, to now we're living in a time in which everyone has a calculator and can get this picture immediately, right? So it's just giving you the picture, I think, or you getting the picture on your calculator is perfectly reasonable. The only issue now is that for me to give you a problem like some of the ones down here in which you don't have a picture, right? Some of the ones down here, like 9 through 14, and to say figure it out, then it basically requires you to have a calculator. We're going to do some of these, and the first thing you'll see me do is graph it. I mean, that's the first thing I'm going to do, right? What does that require? That requires that basically you have a graphing calculator, but then it becomes a question about, do you have the resources to get a calculator, right? I definitely didn't want it to become a question about, you know, can I, because some people just don't have them. Right, they're expensive, right? So, for the record, she stole this calculator, right? Whatever it takes, right? But the point is, I didn't want it to become about that either, right? Now, it is true. IT majors in here? Who are the IT majors here? Anybody? Yeah, right. So now we're forcing you to have one, right? Right? There's a program, a laptop.
I like having cool toys.
Oh, so do I. But you also it implies that you have the resources to get one, right?
Yeah.
Of course, right. So, but the IT program now says that if by your sophomore, junior year, you have to have a laptop, which makes complete sense if you're in IT, right? That makes complete sense, right?
Well, kind of. I mean, I've got an advanced programming class in like a regular classroom, so
Yeah.
not only do I have to have a laptop at home, I come to class without my laptop, and I'm just screwed.
Right. No. Yeah. Right. Absolutely. Right. So, but I did not want the question to become about resources. That's the point. So I'm probably just going to give you the picture. All right. So to get warmed up, let's go ahead and do this one.
So what, you're not requiring one? Does that mean we can't use one if we have it?
No, you cannot use one. Well, there's also some other reasons too, because the calculator can do more than I want you to do with it.
Some of them can solve and stuff.
Hey, absolutely, yeah, absolutely.
How do you figure out the balance without a calculator though, because they're not on it?
Oh, we'll talk about that. Yeah, that's good. That's a good question. Yeah. Right.
Question?
Please.
On the online videos, what kind of video format do you use? Because it's just a black little box for me.
Oh, it's not working for you?
It won't load videos, so I was wondering, like the JavaScript, is it?
It's just QuickTime.
Oh, yeah, it's QuickTime.
It's
Okay.
QuickTime, yeah.
Okay.
We'll have to take a look, yeah. What is that here? All right, so f of x is equal to x. G of x is x squared minus 2. As we said before, it's the integral from something to something, that's right, of x minus x squared minus 2 dx. Of course, the question is, what are these values? Right, so the question is this value here that we're looking for, this goes here, and of course, this one, you gotta be good, let me look here, this one needs to go here, right? Of course, now, again, we'll set them equal to each other and solve. You set them equal to each other and solve as a quadratic equation in our sleep. Hopefully, you'll be able to factor it. I think you can, yeah. So, what is that? Negative 1 and 2? I think it's negative 1 and 2. X equals x squared minus 2. That's true if and only if x squared minus x minus 2 is equal to 0. That's true if and only if x minus 2 times x plus 1 is equal to 0. And that implies that x is 2 or x is equal to negative 1. So it's the integral from minus 1 to 2 of x minus x squared. I'm going to distribute the minus sign, okay, plus 2 dx. Sleep, sleep, sleep in our sleep. I'll take questions about that. I need to move this up a little bit. 1/2 x squared minus 1/3 x cubed plus 2x evaluated from -1 to 1. Of course, this is true by the fundamental theorem of calculus. So this is equal to 2 minus 8/3 plus 4 minus 1/2 plus 1/3 minus 2. Whatever the hell that is, okay? I'll take any questions about this. That's question about this. Question number 6, 7, 8, 15. Do you remember which one this is?
I think you're
At what? No way.
I think so.
No.
We did what? Was this 7? This is 7. Okay, fine. That's good. Okay. But it's 9. You're scaring me. So question number 7, I'll give you a problem and I want you to do it both ways. What do I mean by both ways? With respect to x and with respect to y. This is with respect to x right now, right? But we'll do some ones where you do it with respect to y. So either I'm going to give you one and you do it both ways, or I'll give you 2 and you have to do it each way. Okay. Questions about this?
You said this was with respect to
X.
X.
Everything's written in terms of x, yeah. Let's do another one. Get some more on this. So x cubed. Let's do this one. Now, first of all, let's see. If we were doing this with respect to y, this one will be difficult, right? And the reason is because doing it with respect to y, we're moving from the leftmost function to the rightmost function. But this formulation really isn't nice going from left to right, only because we have some issues here going from left to right. They intersect here, and it's difficult to go from this function all the way to the left because some of the functions under it, right? Here, can we do this with respect to y? Is one function to the left of the other? Right. In pieces, right? So if I was doing this with respect to y, I would have to break this into pieces, right? So we'll go ahead and do that. And I may just take this first half and then double it, right? One can demonstrate because of symmetry that this area is just twice this area. I'm sorry, this area and this area are equal, and therefore the whole area is just twice this area. Okay. So we'll go ahead and do a test question just on this one, a test-like question. Let's do it. So I'll create my own graph here. X and x cubed. Where are you? There you are. Let's get it set up. So here's a test-like question. Put it in black. Test-like question. And again, the claim is that it's number 6, but apparently it could be 6, 9, 30. I have no idea how many questions are going to be on this, okay? Maybe it's number 6. Right, so how are we going to word it? Oh, find the area between the two curves. The area between the two curves. In 2 ways. Is it 7? You believe it's 7? Thank you. So, I don't want you to miss anything, miss a question, or maybe I don't want you to miss one. She thinks it's, wait, you think it's 6, you think it's 7, so you're missing one maybe.
I think it's way further.
You think it's what?
I think it's way further. I think it's like 8 or 9.
You think it's C now? Okay. So, but don't worry, when we start to review, we'll get them all together. Okay.
thought you said, like Tuesday, I thought you said that, one was number 8, but I also thought maybe you skipped 7.
Okay.
I'm lost.
Okay. But wait 1 second. Addie, you're the one who's supposed to have this down. Like in Calc 1.
Well, I know that we review, you go through all of them again.
So you just
Not
stopped.
really-
Okay. Okay. Then the numbers are done. I'm gonna stop keeping count. This is a test question. Period. See, I could trust her in Calc 1. And she would just say, I'd say test the question number, and she would just say it for me with respect to X and with respect to Y. Right, and here are the functions. The functions are f of x equals, well, let's put it in a different color. So f of x equal to the x and g of x equal to x cubed. As a matter of fact, I can just go ahead and steal this one, right? So this one here. I'll just take this first quadrant here. All right, now I could do the whole thing, but it's okay. So, take this, okay,
It's number 8.
Is it number 8? Okay, number 8 it is. Now, you told me the number, but I just abandoned the number. Do you want me to keep count again?
Yes.
Okay, now can I trust you to, thank you. Number 8.
I have it all from day 1. Yeah.
You don't have a number? Okay. Want that volume. I'm sorry. We want that area. Okay. Good. So with respect to x, no problems, right?
Maybe.
Again, where they intersect, x cubed equal to x, implies that x is equal to what? 1. Okay. Now, of course, I have to be technical here. Again, the fundamental theorem of algebra says that there's supposed to be 3 answers to this. Yeah, it looks like 2, but again, we include repeats. Okay, so this is true if and only if x times. Oh no, there are 3 answers, right? Negative 1 counts too, right? Right, so negative 1. So x minus 1 times x plus 1 equals 0. So I'm only looking for the positive in this case. I've imposed that, and only look at positive. So x equals 0, x equals 1, and x equals negative 1. See how the theorem works out for us? Again, we just want these 2. Okay. Very simply, the integral from 0 to 1 of, which one's bigger, x minus x cubed. No problem. We'll do it with respect to y in a second. One half? I think it's 1/2. I'm sorry, 1/4. I think it's 1/4. 1/4. This is equal to 1/2 x squared minus 1/4 x to the 4th, evaluated from 0 to 1, 1/2 minus 1/4 minus 0. And notice again, I'm skipping steps. Feel free to tell me not to do that. plug in 1, 1/2 minus 1/2 times 1 squared minus 1/4 times 1 to the 4th is 1/2 minus 1/4. You plug in 0, everything goes away, right? So 1/2 minus 1/4 is 1/4. Please.
We don't negative one negative because we're only looking at the positive.
Oh, only because I chose to only find this area. That's right. That's the only reason, right? But if you were doing that other problem, then you would have minus 1, yeah.
If
Yeah.
you were using all three, would you set it up -1 to 0 and then 0 to 1?
Absolutely right, because the order changes. That's right. That's right. So yeah, I probably should just do the whole thing. But let's look back at the picture, right? So I hope everybody sees that. That if you were doing this with respect to x, you would do the integral from -1 to 0, and then have x cubed first minus x, and then the integral from 0 to 1, and then x minus x cubed. So now with respect to, we'll put it in a completely different color, with respect to y, put it on a different page. With respect to y, one will write all functions in terms of y, and therefore y equals x becomes x equals y, and then y equals x cubed becomes x equals y to the 1/3. But those are the functions, right? X and x, yeah. Now we're integrating. Now I guess I should say here a is equal to 0. A is equal to 0, and b is equal to 1, right? And now for us, with respect to y, c is equal to. Looking at the picture here, we can set them equal to each other again. C is equal to 0, and d is equal to 1. Oh, I'm sorry, that's the wrong picture. All right, so y is going from 0 to 1. And again, you would get it the same way, and you just set these equal to each other and solve. So y equals y to the 1/3 when c is 0, d is 1, and also when when y is -1. Okay? So we just need to verify that the integral from 0 to 1 of which one is the rightmost no, the rightmost. Right, so it's y to the 1/3, and so it's y to the 1/3 minus y. Right. And we know that's got to be 1/4. Let's just verify it. So automatically you see that doing it with respect to certain letters makes one a little bit harder than the other. I think this one's a little bit harder, only because, dealing with this 1/3 fraction instead of the third fraction, instead of 3, makes it a little bit harder, but not really. But you can see when we step up the level, sometimes for sure you'll want to do things with respect to x and not with respect to y, or with respect to y and definitely not with respect to x. Okay. I think you can see that in the previous problem here, that if we were doing this with respect to y and going from left to right, then it becomes really difficult because it's hard to do this with respect to y because it's hard to go from left to right here. So we wouldn't even do this with respect to y. And that's to do with the fact that x squared minus 2 is not 1 to 1. Right? Let's just say x squared minus 2 is not strictly increasing. get 1/4. This is equal to, add 1 to the power divide, 3/4 y to the 4/3 minus 1/2 y squared, evaluated from 0 to 1. That equals 3/4 minus 1/2. 3/4 minus 2/4. 1/4. I'll take questions about what I'm asking. So again, by the fundamental theorem of calculus, you find the antiderivative, and then you plug in the 1 to 0 and subtract. You plug in the 1, it's 3/4 minus 1/2. Plug in 0, you get nothing. And so it's just 3/4 minus 1/2. Please.
Are you supposed to do the same answer for X and Y?
Oh, absolutely.
Okay.
The volume does not change. I mean,
Yeah.
the volume's sitting there, and now I'm dancing around which one to use. I better get the same answer, right? So, yeah. Right, so that, just in terms of the test question, I really like that, right? So clearly, well, one, it helps you out because you know what the answer should be, right? So I like that. And then two, I mean, it shows your dexterity. I want you to be able to look at one of these problems and say, I can do this with respect to X, or I could do it with respect to Y, and be able to know how to do both, right? So that's why I'm probably going to ask it in this way. Yes?
Will you put the graph with it? Or?
I am going to give you the graph. That was my whole argument, that instead of requiring everyone to have calculators, I would prefer just to give you the picture up front, right? So either I'm going to put it up here, or I'm going to have it on a separate sheet.
Okay.
Now, given the context of this task, there are going to be a number of graphs probably, so I'll probably just have it on a separate sheet, all the graphs that you'll need. Thank you for your question. Other questions about this? It's up to level just a bit. Okay, so now let's just look at these and see which ones can we do with respect to X and with respect to Y. How are we doing this with respect to X, for sure? One graph is clearly above the other. One is really not to the right of the other, right? So that's all we're looking for, right? So if we see two graphs and one looks like it's to the right of the other, or one looks like it's above, then that just tailors, you know, which one you should do. Okay. Here, obvious, I hope, right? That one is clearly above the other, right? So, but the method is the same. You just have to remember the antiderivative of 2 to the x power. So that's a little sick there, okay? So you remember that. Quick review. So there's a function that's been presented to us that we might have to remember. So the review is, first of all, we know that the derivative of 2 to the x is, well, let's step back. The derivative of e to the x is e to the x, okay. It's 2 to the x times the natural log of 2. Okay. Given that the antiderivative of 2 to the x is 2 to the x, of course, if this is the inverse operation of this, you're not multiplying by the natural log of 2, but you're going to do what? Inverse operation, divide by it. Just divide by it. So in general, I didn't write this one, but the antiderivative of a to the u du is equal to a to the u times 1 over the natural log of a. So whenever you come across, now again I have to make the argument, and hopefully this argument was made in Calc 1, but the base we use most of the time is e, right? And because of the change of base formula, we can always change to another base, right? And all you do is end up multiplying by a constant. But we like the base of e because e is the only base, so that the derivative at 0 is equal to 1. Okay, so we like e for that reason. But of course, in biology and cell division and all that other stuff, the base of 2 is often important. Obviously, the base of 10 is important as well. So other bases are important, but in the calc context, we usually just use e. And then here are a bunch. Here are a bunch where it's just like, you sketch the region, you find the area. Okay. So here again, this plot, and you're doing the same thing as these other ones, okay? Any ones that are interesting, let's do 13. So the region bounded by that one. Yeah, let's do 11 and 13. I thought we just did x and x squared minus 2. Didn't we do that? Yeah, okay. So they gave us that picture and they asked us again, right? Yeah, okay. So 11 through 14. We'll just click off 11 through 13. And then we'll just note that that one's been done. Looks like all of these are good. So we'll do a couple of these, and then we'll do some with respect to y exclusively, and then we'll get back to rotating around axes. E to the x, e to the minus 2x, and x equals the natural log of 4. All right, so let's get a picture of that. Plot together e to the, here we use the exponential. The exponential of x, the exponential of minus 2x, and x is going from, did it say 0? Did it say the y-axis? What was the description? E to the x, oh, so they only say this. They're not saying a lot here, okay, so let's see what this region is. All right, so I'm going to assume x, we'll see in a second, x equals, let's say minus 10 to the natural log of 4 to get an idea of what region they're talking about. Okay, so there's a syntax error here. Oh, x equals negative 10 to the natural log of 4. Okay, I don't think they mean that, right? So let's just try 0. I think they mean that. Oh, they intersect at 1. They intersect at 1, right? At 0, they're both 1. So they mean that region. Okay. You can demonstrate analytically that one is higher than the other. Obviously, e to the x is higher than e to the minus x. E to the x is increasing, e to the minus 2x is decreasing, simply because of the plus and minus signs, respectively. Okay. One of the functions, well, one of the graphs that's not here is the line x equals the natural log of 4. That is this vertical line that we are not putting here. Vertical in some universe, okay? I'm trying. And so here's x equals.
Snaps vertical. That's vertical.
Say it again?
It snaps vertical. That's vertical.
Yeah. So Mabel doesn't put that in pretty well, but this is x equals 4. This is e to the x increasing. This is e to the minus 2x. Let me go ahead and be good with my colors here. So this is e to the x. This is e to the minus 2x. This is x equals 4. Let me go ahead and put this outside.
X equals natural log of 4.
I'm sorry, that's right. The natural log of 4. Thank you. And of course, if we have a color left over, it's blue, and we're just looking for all of this. Again, specifically, this has to be with respect to x. Okay, it's hard to, if they meet like this, it's hard to do. This is certainly, one is certainly not to the left of the other. Okay. This probably be one of the last ones we do. The integral from, looks like x goes from 0 to the natural log of 4 for sure. E to the x minus e to the minus 2x dx. This is equal to, by the fundamental theorem of calculus, e to the x plus 1/2 e to the minus 2x, evaluated from 0 to the natural log of 4. Now we said when we take the antiderivative of e to the lambda x, the answer is e to the lambda x divided by lambda. Right? So you have to divide by the negative 2. So it's e to the x, and then it's the antiderivative of e to the minus 2x is e to the minus 2x divided by negative 2. So that makes it a plus 1/2. But if you don't see that, go ahead and make u equal to negative 2x. du is negative 2 dx, and then dx is minus 1/2 du. And then you get the minus 1/2 to come out. Right? So you can go from here to here using the chain, the substitution rule. Right? So again, e to the natural log of 4 plus 1/2 e to the minus 2. Whew. See what happens when I go too quickly? E to the minus 2, the natural log of 4. I'm worried about this being positive to start, but we'll see. Minus 0, e to the 0 plus 1/2 e to the 0. And so this is e to the natural log of 4, and then we'll just remark that this is plus 1/2 e to the natural log of 1/16 minus 3/2. Okay. How did I get that? So this minus 2, we can make the power of 4. Right. So the natural log rules. You can bring this minus 2 over and make that the power of 4. 4 to the minus 2 is 1/16. 1 plus 1/2 is 3/2. The point being, oh, by the way, you can leave it like this. You can leave it exactly like this. If you left it like that, well, this is actually stretching it. You can leave it like this, maybe. Right, so, but you need to simplify that. Okay. 4 plus 1/32 minus 3/2. That's a nice positive thing. Okay. That's the area, unit squared. Questions about that? I'll leave the other one to you. So this one we did. This one's done. That was the first one we did. We just did this one. I'll leave that one to you. It's the same thing. Any questions about these? Let's do some strictly with respect to y. It's not that big of a deal. Okay, and then we'll do some. That's the region bounded by y equals sine, y equals cosine, and the x-axis between x equals 0 and x equals pi over 2. How will we handle this area? They're calling this a compound region, okay, because they haven't gotten to the y problems yet, okay? How about we do this? So some people would split this up here, right? Right, and just calculate the area under sine, and then add it to the area under cosine. And so ones that intersect like this again, this is sine 2x. Sine 2x first from 0 to wherever they intersect. We need to find out where they intersect. And then from that point to this point, that looks like pi. Okay.
Would we have something like that on the test?
Something like this?
Yeah.
I mean, I would give you the picture. But if I give you the picture, would this be okay to be able to do? Right. Then it just becomes almost a trick problem, which of course scares people, right?
Yeah.
So, okay, then let's go ahead and solve this one. So we want to do this one. So this is not a question about anything except for what the hell is this number, right? That's all we're trying to figure out. Everybody knows how to integrate. Everybody knows how to subtract the two functions, right? So what is that number? Okay, so question is, what is that? So we need, I'll keep it in red, so we need the sine of x to be equal to the sine of 2x. There are a couple of ways to do this. All right, you can do this by inspection. Where is the sine of x equal to the sine of 2x? That's the sine of x, sine of 2x. Let me see. We need to bring up a unit circle. So I need the sine of x to be equal to sine of 2x, right? So we need an angle. See, and the bad part is you're all going to make me draw a circle. That's the real bad part. Okay, here we go. Oh, you know what? That's about as good as it gets. I just said, what the hell? Let's just draw something, okay? No, I'll try and draw something better. What's funny is they don't have a circle drawer here. I don't. I'm not sure, but I haven't found it.
What's that circle in square?
Oh, what about this one?
Yeah.
Wow. So what happens now? So is this going to give me the center, or is this going to? Ooh. Let's undo that because we need to be in the center, right? So. Okay. So the sine of x is equal to the sine of 2x. The sine, of course, by definition, is what coordinate? It's the y coordinate, thank you. And so that we need the y coordinate for an angle and twice the angle to be the same. And that is here. Right. Well, what is that? What angle is that? Not 45, because the sine of 45 and the sine of 90 are not the same. Pi over 3, right? The sine of pi over 3 is one thing, and then 2 pi over 3 is over here. So it is pi over 3. So that's the by inspection example, right? But then you can also do, what'd you say?
There's no way I can figure that
No way? Okay. That's fine. Sine of x is equal to, and then, well, this is the way you would have done it, right? Sine of 2x is 2 sine x cosine x. Is that right? Yeah. Junior year of high school. Right, so the observation is that the sine of 2x is 2 sine x cosine x. Okay. We're going to really need to know these, okay? Sine of 2x is 2 sine x cosine x. And then you can go ahead and factor, right, or bring everything on one side. Do not divide by the sine of x. Okay, they both have sine x in common. And then it's 2 cosine x minus 1 is equal to 0. This is true if and only if the sine of x is equal to 0, or 2 cosine x minus 1 is equal to 0. That's true if and only if the sine is 0, or the cosine of x is equal to 1/2. And that happens at 60 degrees, which is pi over 3. So you get x equals pi, or x equals pi over 3. Now, why is it that we don't have 2 pi here? Why don't we have 2 pi as one of the answers? Yeah, because it was only going from 0 to pi. Because just the context, right? The only one on the interval 0 to pi. Okay. So cosine x is, I'm sorry, pi over 3, right? I eventually catch myself. Maybe that's why no one corrects me. He'll figure it out. So x is pi over 3 or x is pi. So now that we've done that, no problem, right? So it's the integral from 0 to pi over 3 of, which one's higher? Sine 2x minus the sine of x. Sine 2x minus the sine of x dx, and then plus the integral from pi over 3 to pi of the reverse, sine of x minus the sine of 2x. Yeah, it really does look that bad. I looked at the screen. Yeah. Okay. Plus the integral from pi over 3 to pi of the sine of x minus the sine of 2. Keeping me in check. Thank you as always. In my Calc 1 class over the summer, I think the craziest one, I think you said, was that a Q? And it was like 3 or something like that. Yeah, that's right.
I've gotten 10 classes and I still like.
Right. No, it's part of my fault too. I don't even want to do these anymore. I'm getting hard on you now. These, we're about to get these down cold now. Okay. How many integrals do I have to do until you're just like, please, no more? Right. Please, let's just do it. Right. So antiderivative of sine 2x, antiderivative of sine. We should just be able to have these cold now. I can't be in my right mind because I've been doing antiderivatives and integrals, for a decade and a half. So I'm slightly getting tired of them. Okay. But I had always wondered, and I always mention this, I guess, that at my old school is a much older school, 1867 school started. And there were people there who had taught for 30 years. And I was like, how in the world can you teach the same thing for 30? I mean, what? Right? And I said, well, I seem like I'm on that track, but it's not so much about the subject, but it's the people, right? Classes are completely different. The audience is different, right? And so that makes the class completely different because you get different questions, right? So the worst thing is when you all are quiet, right? So if no one ever asks questions, year after year after year, if no one ever said anything and I'm teaching the same material, then I would just jump off a bridge. I mean, it would just be ridiculous, right? But the personalities that you bring actually do make the class much more interesting.
Your teachers, they're like, oh man, I want to go to my Tuesday, Thursday, this sucks. And then when I tell we're like, oh, I hate it.
That's what I'm saying. We talked about this earlier. We feed off of each other. If you all suck, then the class sucks. I'm serious. If I suck, the class sucks. So we both need not to suck. All right? It's just that simple. Right? All right. I'm taking any questions on this. Negative 1/2 the cosine of 2x, right, plus the cosine of x, evaluated from 0 to power of 3. Take any questions on how I get that. And then minus the cosine of x from power of 3 to pi. And then plus 1/2 the cosine of 2x from, oh, well, actually I could put it on both. I'll put them on Let's be uniform. I'll put it at the end. I could put it on this immediately, but I'll put it at the end. And so, power 3 pi. And just plug all that stuff in. Okay. All right, I'll take any questions about that one. Right. So again, that one wasn't so much about, but I won't ask you anything like that. No, I'm not gonna ask you. Yeah, I'm not gonna ask you anything. Because again, it doesn't even become a question about whether you know the calculus. It becomes a question about something else, and I'm asking calculus questions. Okay. Right, so more graphing on your own, and then they claim these are with respect to y. We'll do a couple. With respect to y, x plus 8. I'll take this one. Here, one graph is certainly not above the other. One is to the right of the other, and therefore, we're going to integrate with respect to y. Okay. But of course, we're going to give it to you with respect to x. So most of the time. So since one graph is to the right of the other, then with respect to y. X equals y minus 8, and x equals 1/2 negative 1/2 times y minus 8. And that is minus 1/2 y plus 4. There's some numbers we don't know, okay, for y. So y goes from here to here, so we just need to figure out that value there, okay? The integral from something to something, rightmost value is this one, 8 minus 2x, but that corresponds to minus 1/2 y plus 4 minus y minus 8 dy. So the question, of course, of what are those values? Right? So one is obviously 0, given the context. And then we'll set these two equal to each other and solve. As a matter of fact, we can do this in either way. We can set these two equal to each other, solve for x, and then figure out what y is, or we can just set them equal to each other in terms of y. Right? Let's just do it in terms of y. We're changing everything with respect to y. Let's just go ahead. Do that. 3/2 y equals 12. Add 1/2 y to both sides, that gives you 3/2. 1 plus 1/2 is 3/2. And then 8, y is equal to 8. Multiply both sides by 2/3. 2/3 of 12 is 24 over 3. 12 times 2 over 3 is 24 over 3, which is 8. This is the integral from 0 to 8. And then, again, you should have no problem going through that. So by the fundamental theorem of calculus, this is equal to minus 1/4 y squared plus 4y minus 1/2 y squared plus 8y evaluated from 0 to a. That 8y is plus because I'm minus into minus. Put equals here. Just find the areas. Plug in 8, 0, and subtract. You plug in the 0, everything's gone. Minus 16 plus 32 minus 32 plus 64, 48. Eight squared is 64. 64 over 4 is 16. Minus 16. 4 times 8, 32. 8 squared, 64 over 2 is 32. And then 8 times 8 is 64. And then 32 is canceled. 64 minus 16 is 48. I got some sleep last night. At least know, 16 minus 10 is equal to 4 today. All right. Questions about this? Okay, I hope we have the basic idea. I'm going to give some homework on it. Let's just look at a few others to talk about game plans. Hopefully this is straightforward. Okay, so how will we set this up? That's right. The integral. Tell me what the integral is. The integral from where to where? Where's y doing? From 0 to 2. The integral from 0 to 2 of this one's kind of tough, right? 2 minus the natural log of x. So you're doing this. Now, is this do this with respect to y? With respect to y. Okay, so it should only be with respect to y. Say it again? No x's with respect to y. So y equals the natural log of x. Uh-oh. Let's go ahead and do it. From 0 to 2 of what? What would we do? What's so interesting, of course, is that literally, well, we'll do it in a second. Well, let's do it now. If I had given you this, right? If I had given you this one, why am I doing that? Alright, we're having a lot of fun today. Yeah, I did get some sleep, I swear. I'll use this one. Yeah, we'll use that one. So this, right, and then this. If I give you this here, okay. Yeah, if I give you this, and made that x equals 2 and called this y equals e to the x, no one would have a problem with that. If I wanted to know this area, right, then everybody gets that. Right? But this is just that on its side. That's all it is. Right? So if y is equal to the natural log of x, tell me what x is by definition. For sure, it's e to the y. So all this is e to the y. Because all this would just be e to the x. It's just the integral from 0 to 2 of e to the x, right? So this is just turned on its side. And so again, switch everything in terms of y, and then the rightmost value is 0. I'm sorry, the leftmost value is 0, and the rightmost function is e to the y. All right, so it's e to the y minus 0. Oh, well, and this is just e squared minus 1. So this is just the antiderivative of e to the y is e to the y, evaluated from 0 to 2, e to the second minus e to the 0. All right. And in any way you like, two approaches express, and here's how the test question is, right? So express the area of the following shaded regions in terms of A, one or more integrals with respect to x, and B, one or more integrals with respect to y. Oh, you don't even need to do them. Okay, so they're being nice. Whew, some of these are serious. All right, so what's going on here? How do you do this? How do you get this area? We'll do 27 and then we'll be done, okay? We'll be done with this section. You look at this immediately, you say, okay, I want to do this with respect to what letter? Right. Is one, so the first question you ask is one above the other, or is one to the right or the left of the other?
Yeah, so y.
It's y, right? This is to the right of this one. So initially we will want to do this with respect to y. And if we did that, then we need to know, oh, they're using this picture again, that's interesting, but they only want this area. So now we need to know this value, where they intersect, and we found that to be -1, right? So that's -1, and where's this 0? On the left-hand side. Where is x squared minus 2 equal to 0? Yes? So x squared is equal to 2. So x is equal to square root of 2 with a plus or minus, right? And clearly this is minus the square root of 2, right? And so then it becomes, now we need to switch the letters, right? So instead of having y equals x, it's x equals y, and then here it's x squared is equal to y plus 2, and then x is equal to plus or minus the square root of y plus 2. Okay? And so here, we're taking this graph, right? And here, which one is it over here? Is it plus or minus over here? Minus. X is negative over there. Right? So it's the negative. Okay? And so finally, the integral, y goes from where to where? When x is -1, so it looks like -1, y goes from -1 to 0 of the rightmost one is y minus the negative square root of y plus 2. So with respect to y, this looks bad. I don't think it looks any better with respect to x. Okay. Questions on that?
Why did you go from -1 to 0?
Oh, so what are the y values This is with respect to y. And so
Oh,
the
okay.
y value here is -1, and the y value here is 0. Yeah. So with respect to y.
So does negative square root of 2, where does it come into play?
Oh, that was the x value,
Right.
right? So really, that was in preparation for doing it with respect to x.
Okay.
Yeah, because we were about to do we were about to do both ways. Yeah. Okay. And so you don't have to evaluate it. They just wanted to see this. Right. But if you did evaluate it again, use substitution. U is equal to y plus 2. Du is equal to dy, and you're able to do it using the power rule. All right, so that's with respect to y. With respect to x, we'll put it in a different color. Right, so with respect to, well, I should do it this way. With respect to x, and now in parentheses I'll say I'll abbreviate that with respect to. What happens now? What type of crazy stuff we're going to have to do? So brand new picture. Let's bring it down. What are we going to have to do now? How do we rectify this area here? I'm just going to have to just deal with this, right? I have to do an area from here to here, and then the area from here to here. I don't have a choice. Okay. And so then I find this area, and then I find this area. Right. They intersect at -1, and so it's the integral from, we found that other number, right? It was minus the square root of 2. The integral from minus the square root of 2 to -1 of 0 minus, what is this? X squared minus 2 dx. And then plus the integral from, that was -1, right? -1 to 0 of, which one's bigger now? It's still 0 minus x dx. Okay. Actually, that one is easier, I think, to do. Right. Is that okay? So that's what it would be with respect to x. Again, I'm not going to be giving ones that complicated. At least I don't. I mean, if I do give ones that's complicated, you just have to write the integral, and you don't have to evaluate it. Even though the integrals you can easily evaluate. Right. Questions about that? So on the homework, I'll give you some in which you just have to, probably not evaluate, but just write what the integral would be. Like that. Okay. All right. Any questions about integrals? Any questions? Any questions about finding areas between two functions? And any questions about what I will be asking on the exam? All right. Let's keep rotating. Now we ended with the sine of x. Is that right? The last function we did that we were rotating around the x-axis. All right. Let's go ahead and do that one. So 6.2. Find the volume obtained by rotating sine of x on the interval, it was 0 to pi, on the interval 0 to pi around the x-axis. And we had that picture up before. I don't have that, so let's plot it again. So let's plot the sine of x. X equals 0 to pi. Okay. So it's that. And very basically, we said that in general, that the integral of any function, or the volume of any function rotated around the x-axis is pi times the integral from a to b of f of x dx, f of x squared dx. I'll go ahead and rewrite it. F of x all squared dx. And the way that we get that again is we take a rectangle. Oh, now I have some options here, right? To actually draw reasonable rectangles. Right. So, oh, is this going to give me the center, or is this going to give me the corner? We'll see. Okay, very nice. So we take that rectangle here, rotate it around the x-axis. That's going to give us a disk. And let's see if I can get out of drawing this disk. I don't think so. So let's see if we can do something like this. So we get this disk, right? And then we get, oh, let me just do another one, right? So we get something like that, okay? Something like that. Okay. It's supposed to be vertical. I'm still working on it, okay? So you rotate this around the x-axis, you get one of these, okay? So this is in black. This here is delta x. The width is delta x, right? The height is f of x, right? And how does that translate here? That means that this distance is what? F of x. Or y, and that's right. So y equals f of x. So that's the y distance. And then this here is delta x, right? And so the volume of this object is one of the many volumes I need to add up to get the whole volume, right? And so pi r squared h is the volume of any cylinder, and so it's just pi times the radius squared times delta x. And I need to add them all up. And again, by the definition of the integral, that just turns out to be this. I need to sum integral. I need to sum all of the volumes infinitely. Okay? And so the real question is, what is the integral from 0 to pi of pi times sine squared x? And again, if you don't see the picture, please come see me after class so we can just go ahead and get a good visualization of it. As a matter of fact, let's go ahead and do that now if it's not clear. We got some tools. Calc 1. Do some volumes, right? Volume of revolution. We're going to take the sine of x. From 0 to pi. Okay, so sine x. Oh, do I need to turn this off? Right, so sine x from 0 to pi. Notice how they have a g of x here, because we can find the, we're going to find the area between two regions and rotate that around the x-axis. But for the moment, it's between sine of x and just the x-axis. Right, so the x-axis is y equals 0. I don't need to put it, but I'll put 0, okay? And then we can do some, when you construct these rectangles, you can use whatever method you want. And then we're going to display the disks first, okay? And it's around the x-axis, and so the line of revolution is horizontal, all right? And so each one of these, so there's 0 to x, you get a disk for each one. Right? So there's the sine of x, right? And you rotate it around. So they broke it up. How many? It looks like 4, right? No, 6 rectangles. So they broke up the interval 0 to pi into 6 rectangles. 1, 2, 3, 4, 5, 6, right? And then when you rotate each one around, you get this disk, right? And then you add up the volumes of each one of those disks, right? please, pi squared over 2. That's what they get. Right? So it's not obvious how they get that. We'll do that in a second. Okay? The question's about the picture. Right? So there's the XY axis. And then when you rotate it, you just add up the first this, the second, third. Actually, that's the last one. First, second, third, fourth, fifth, and sixth. Right? And obviously, the more you take, the better it becomes. Right? And so that if we look at the actual answer, it's that thing. Okay. Oh, please, sir.
It looks like, I mean, for this, does it not matter what points you use, like the left point, midpoint?
No, it doesn't matter. That's right. So there's a theorem that says that if f is continuous, it's not about the method, it's about the number of rectangles. If you take enough rectangles, it doesn't matter the method. Right? So that was the first thing we said about the integral on the first day. It doesn't matter the method, it matters about are you taking enough rectangles, and it's going to always work out.
Well, on that picture, it's the one where you had 8. It had
8, yeah, let's go ahead and put this. 8.
It just has, it has all of them.
Yeah.
On the right side, they use the right point. On the left, uses the left point.
I feel like it's using the midpoint each time. It's hard to see.
That's right there,
It does
method,
say
midpoint.
It is the midpoint method, yeah.
Okay.
So I think like this height looks like it's the midpoint of this interval. This height looks like it's the midpoint of this interval. I think it's the midpoint method, yeah. Yeah. Right. But again, the answer, I mean, and this is correct. Look, I only use 8, and it's correct. It's correct to all the decimal places. The approximation. Okay. So the midpoint is actually really good here. If I use the right endpoint method, it's going to be off a little bit, right? Maybe not. That's interesting too. Right? So display that. That's interesting. That's still exact. Wow. So a ton of decimal places, all right? And what does that mean? That means that the amount in which you're under approximating is made up over here where you're over approximating. Okay. Because
Sine is symmetric.
right, because sine is symmetric. Sine is symmetric over the midpoint, which is pi over 2. All right, fantastic. Now, how do we do this by hand? Right. So then the observation is, and we'll do a number of these in chapter 7. The observation is that the sine squared x, more trig, is 1/2 minus 1/2 the cosine of 2x. I guess that's a remark. The remark is that. And now that we have that, this is a problem we can do. And so now this integral becomes pi times, now again we have to get, what's the answer again? We have to get pi squared over 2. All right. We'll put that in parentheses here. Pi squared over 2. So if that's true, then this becomes the integral from 0 to pi of 1/2, which we have no problem integrating. And the cosine of 2x, we have no problem integrating that too, as long as we end up dividing by 2. Right, so this is equal to, by the fundamental theorem of calculus, pi times, I hold the pi on the outside, 1/2 x minus 1/4 the sine of 2x. Right, the antiderivative of cosine is sine, and because of this 2, I have to divide by that 2. And then I'm going to evaluate that from 0 to pi. Plug in pi 0 and subtract, this is equal to pi times 1/2 pi, and apparently everything else goes away, minus 1/4 the sine of 2 pi, minus 0 minus 1/4 the sine of 0, but again, all of that's nothing. And this is equal to pi times 1/2 pi minus nothing. And that is pi squared over 2. about that. So the observation, once you make the trig observation, then it follows pretty straightforward.
Could he have set signed x as your u, done u squared?
Where? So you're saying
Before the remark.
Before the remark. Oh yeah, you could be sine. You could be what? Sine?
U, yeah.
U is sine. Where's du? Du's cosine. There's no cosine to be found, right? Yeah. Yeah. So obviously we look at this, and the first thing we say, just like he said, is can we substitute? I skipped that step, but because it's obvious you can't substitute. If u is clearly sine is inside the squared function, so you would make u equal to sine, but d is cosine, and cosine is nowhere to be found. Then we just have to conclude that this function did not come about because of the chain rule. We did not use the chain rule to get this function, and therefore we're not going to use substitution to find the antiderivative. Let's look at some of these exercises. 2, S6, 5. I was trying to be ambitious today, right? So this is the dis method. So again, rotating. It's rotating around. So when you rotate around, you get this disk, right? So you've done this a number of times. I hope it's obvious at this point. And we're just going to add them all up. We wrote this last time as a remark. The dis method about the x-axis is just pi times the function squared. The washer method, so a slight variation on the dis method, allows us to compute more exotic solids of revolution. Okay, so there's F, and there's G, and now we want to rotate that around the x-axis. So a washer in this case is a disk with a hole in it. Okay. How are we going to get that volume? Well, you just find the volume for F and the volume for G, right? Right. So the whole comes about by what? By subtracting, for sure. So in order to do that, we just subtract. So that is the method. So you want to find the volume obtained by rotating the area between two curves. You just take the difference in the squares. So we'll go ahead and we'll use that one. We'll do an example. I hesitate in calling this question number, but now we know. Question number 9, thank you. Now, did we already assign this other one? So you're going to find the, so what's question number 8? Perfect. Okay, perfect. So question number 9 is find the volume of the region. Right, find the volume of the region obtained by rotating around the x-axis. There's a whole method about rotating around the y-axis, but then that's a complete function. Then the functions there are functions of y. If I give you a function of y, right, I can rotate it around the y-axis using the dis method, and it's the same thing. We talked about that last time too. Oh, let's put it. So, question. I guess we should put it. There's no room here, right? Let's put question number 9. Find the volume. The region obtained by rotating F f of x on the x-axis. Now it could be g of y around the y-axis, okay, but it's the same thing. All right. And I may give you a picture for those too. Given that, let's go ahead and find such examples in the exercises. Alright, so for this method, we did this one last time. We did y equal, I think it was y equals x, right? But y equals 2x on the interval 0 to 3. You rotate that around the x-axis, it gives you a cone. We already know the volume of a cone, and therefore we can verify that that's the case. So we did that one last time. Here, and they're being nice. Again, another cone. Let's do e to the x. Rotate e to the minus x around the x-axis. Let's do that one. E to the x. Again, we use the exponential in Maple. E to the x, and then from 0, was it the natural log of 4? Thank you. The natural log of 4. Display that. All right. Obviously, pi times e to the x squared. 15 pi over 2, they claim. Okay. See if you get that. 15 pi over 2. Now, the approximating sum is not good here because we lost the symmetry you spoke about, right? So that when we do 8 rectangles with the left endpoint method, right, we get about 19.7, right? So that's not enough. But again, regardless of the method, if we just do enough, I don't want it to go crazy on me. We get a little bit closer, but still, I don't think that's good. That's within 10%, right? But that's still not close enough to, at least in my mind, I want to be closer, right? So maybe we do another method, right? So again, numerical analysts struggle with this all the time. That's much better, right? Right? So numerical analysts struggle with this all the time because, again, they're computing, and you as an IT major understand this, that a numerical analyst is trying to figure out what is this integral. I can either pick a bad method and just make the computer do a million rectangles, but that takes up too much memory to do that, right? So I should spend some time trying to find a better method so that I can use less rectangles and use less computer memory, right? Right. So it's a battle between the method and how much computing processing time. Now, back in the day, before Moore's law really started to kick in for us, we were only concerned with finding the best method because our computers were bad. But now computers fly, so who cares what the method is, right? It's almost like that now, that our computers go so fast that the method almost doesn't even matter, right? So for the left endpoint method, sure, it's worse, but, I guess I can just use, 80 rectangles, right? And it's still not that good. 80 rectangles with the left endpoint method is still not as good as the midpoint method with, how many did I have? 15 or whatever? 19, right? But notice that, what's the difference between, 1.2 seconds and 1.3 seconds for the user, right? It only takes a little bit longer for the computer to do it, right? So that's the evolution of numerical analysis because of the improvements of processing power. But for really difficult problems, it still matters. Right? For really difficult problems, it still matters, whether you're going to do this versus the method. Okay. Right. So the integral, it gives it to us. The integral from 0 to, now they had the 2 times the natural log of 2. That's equivalent to the natural log of 4. Right? 2 times the natural log of 2. You can bring the 2 up, and it's the natural log of 4. The integral from 0 to the natural log of 4 of e to the minus x squared dx, that's flat out the formula. This is equal to the integral from 0 to the natural log of 4 of e to the minus 2x dx. Right? And this is equal to, by the fundamental theorem of calculus, minus 1/2 e to the minus 2x. Again, because of this minus 2, you have to divide by it, evaluate it from 0 to the natural log of 4. Plug in the natural log of 4 and 0 and subtract. And we're supposed to get what? We're supposed to get 15 pi over 2. Oh, what happened to my pi, right? Pi. That equals pi times, plug in the natural log of 4, minus 1/2 e to the minus 2 natural log of 4 minus 1/2 e to the 0. Seeing 15 pi over 2 yet. Pi times minus 1/2 okay, so e to the minus 2 natural log of 4 is e to the natural log of 4 to the minus 2, which is 1 over 16, plus 1/2. Okay. And then, do I see it now? Have I been saying this wrong? Oh, because I put in the wrong function. Maybe that's why. That's a minus. Okay. 15 over 32 pi. All right. Now all is right with the world. All right, so then this becomes minus 1 over 32 plus 1/2, and that is 15 over 32. Minus 1 over 32, 1/2 is 16 over 32, and that is 15 pi over 32. So it's straightforward. Listen, the only issue is practice. Are you going to get all your minus signs right? You're not going to make any mistakes, right? And the only way you can do that is by practicing. So practice, practice, practice. Right? Questions about this or any of the concepts? Okay, good. I'll leave this out. Anyone still writing? Oh, please.
Can you go over the process of where it's e to the negative 2 natural log of 4, how you got e to the natural log of 1 over 16?
Oh, absolutely. So, thank you for your question. So, we'll put that, the derivation for this, you mean this to here? Right, so we'll make a remark. Right, so this comes from that e to the minus 2, the natural log of 4, is equal to e to the natural log of 4 to the minus 2. Because you can bring the power in front here. Right? So that's a rule for the natural log. But this is e to the natural log of 1 over 4 squared. But that's e to the natural log of 1 over 16. And then we'll remark pretty quickly that the exponential and the natural log begins with an I. Inverses. And therefore they cancel each other out, and it's 1 over 16. And that's how we get 1 over 16. And then 1 over 16 times 1 over 2 is 1 over 32. Oh, okay, we'll stop there. All right, so next time we'll start doing some areas in between, and we'll rotate those around the x-axis. Right? That'll take more than 8 minutes to do. so I'll let you go early. I'll put up some homework tonight so you can practice.